Just shout louder, right? I hope I'm successful enough. So, the summary of the whole meeting, the whole week of all these interesting talks. When Axel suggested that I do it, I first thought that it's a real challenge. It's one of the, which can be compared, one of the labors of I think it's the fifth labor, right? And then I thought, well, but reasonable challenge, you can meet it. No, it just means that you have to make an effort. So I thought, of course, that a good friend would never have done anything like that to me. But still, I thought that I should try. But when the conference started, I realized that it's not the right comparison. The right comparison is with the colors. And I like the interpretation of the story of the colors here on this page. It's a landscape with the fall of the colors. Everything is as usual. And the colors is here. So, the person who wants to summarize is here, and nobody cares. So, you first fail miserably after enormous effort, and still nobody cares. I realize that this is the right analogy with what Axel asked me to do.
You're still in the air.
I'm still rising. I'm now in the ascending branch. I'm now ascending. So, I'm trying to do impossible now. So, the range of objects discussed obviously matches the general nature of the theory which was the reason for us to be there. So, the newcomer, relative newcomer here, is the liquid metal experiments. Some 10 years ago, the list would be shorter. The list would contain maybe 3 items. Now, the list where the mean field dynamo theory is successfully applied and tested now includes experimental work, the classical applications to the Earth, the Sun, and then extension to the stars, and then we had a talk about supernova stars, about the events not perhaps related to mean field dynamo, but still fascinating events which occur at millisecond time scales during the explosion of supernova, implosion and explosion of supernova stars. And then interstellar medium of spiral galaxies, and then the cosmological magnetic fields, where we had a very powerful message that magnetic fields magnetic fields is a very subtle dish. It requires to cook it well, you need the best ingredients. You cannot build magnetic fields from a garage. So it was a powerful message of this work. So the objects cover virtually the whole universe. The objects covered in this meeting. The physical concepts, we discussed both the core concepts of the mean field theory, and plus many very interesting extensions. Well, not surprisingly, the magnetic helicity constraint was mentioned in many talks. And I remember quite clearly, in 1992, something like 5 years later, in the mid-90s, the word dynamo became almost a swear word. And people would deliberately change the titles of their papers to get them published. Paper with the word dynamo in the title would have difficulties in being published. It took 10 years to resolve the difficulty, and now the pendulum has swung back to normal state, where we do appreciate that perhaps we don't know how exactly the mean field dynamos work, but we are confident that they do work. It's not about, the problem is not to decide whether mean field dynamos work or not. The problem is to decide how they work. And this is an important change. It's a very important change. In mid-90s, the atmosphere was entirely different. An important subject is MHD turbulence. Surprisingly, even though mean field dynamos are turbulent dynamos, there is not much link to modern theory of MHD turbulence as such. And I think it's very important that we had this really very interesting talk today. It was this morning, right?
Yesterday.
Was it yesterday?
Okay.
Wow, I was looking hard. So, I don't know how this link should be established and how it should work, but I think everybody will agree. There must be closer link between mean field theory and modern understanding of energy cascades, holistic cascades in MHD turbulence, including the anisotropies. Several extensions, interesting extensions of mean field theory. For example, I was really surprised in this growth of interest in this oscillatory alpha squared dynamos. I always consider alpha squared dynamos as something like a poor relative in the family of dynamos, something which is conceptually beautiful and interesting, but in reality can never be important because alpha omega dynamo always wins. And then, so I was really pleasantly surprised to see that it can be important and moreover it can be dominant even in nonlinear state. Again, nonlinearity brings unexpected things. It's beautiful, it's fantastic. It's very good that most of the talks during this week will concentrate on nonlinear aspects of the theory, where you get something which is totally unexpected. The effects of compressibility, they can be sometimes, in some cases, for example, in galaxies, they can be, well, perhaps even dominant. In other cases, they'll be subdominant, but still can be significant. Cross-helicity, there is a sort of constant, not very active, but still interesting cross-helicity effect. But my feeling is that they haven't been understood completely. It's a fruitful area to apply that effort. And then it's a continuing story of higher order mean field effects. During our last meeting, I remember how this omega cross J effect was very hotly debated. So they will always be the case. The longer we leave, the further along the Taylor expansion we should be moving, discovering again new and new subtle effects. And then this negative ionic contribution to turbulent pressure, this week it received much more attention than I ever saw before, which is very nice. It can be potentially very important effects. Well, and this is what Uriel was telling us about, well, the enormous effort he invested in exploring the artifacts of numerical approximation. It is useful. It is useful because very often, if the artifacts take the appearance of interesting solutions, structures, turbulent structures, then it's especially dangerous. Now, I will try to make a brief review of individual objects where, in liquid metal experiments, there was a significant progress in rotational and Taylor instabilities, and also this measurement of turbulent diffusion. I will return with, but you know what worries me slightly is the emptiness of this slide. There are too few lines here. It's important for all of us to make this list much larger. We need to discuss and develop ideas for future experiments, for the years to come, even not for weeks to come. It would be very important. Perhaps I have forgotten something, but I would definitely think that it's very important for all of us that this slide is the longest of all slides of this slide, rather than the shortest. In geophysics, in application to the Earth, there were classical and beautiful examples of this core mantle coupling, which is presented by Paul. reversals, as ever, attract attention. And again, here we are still restricted to discussing models which just mimic the phenomenon. Still, the goal is elusive. Your results with Gary Latsmeyer is perhaps it's one of the very few examples where reversals could be studied almost as a real phenomenon rather than a model which has been constructed to reproduce reversals. So I think there is, as usual, lots of activity here. We should continue. Radiating convection, again, it remains an important subject. In solar and astrophysics, I was really pleased to see what I haven't seen since a very long time ago with various conferences. How what we assume happens in the interior of the sun, how it comes to the surface. Because this is the key. The observations are, most of them, except Halley's cosmology, are at the surface. If you want to compare your theory with observations, you must discuss what will be the surface manifestations of the events happening in the interior. Therefore, I think it's a very important and fruitful direction to develop. This discussion of the emergence of magnetic structures should follow, in my opinion, the development of the physics of the deep interior, one-to-one. They should develop together rather than separately. Otherwise, the two can diverge, and we can spend enormous time discussing processes in deep interior, which in fact have nothing to do with what is observed. Additional effects were added to the whole picture. Relevant buoyancy, thermal instability were added to the dynamo action in the sun galaxies. Miracle circulation. Now, again, one of the reasons I think that the importance of the circulation is again connected, maybe not directly, but there is a connection, I think, with the emergence of the structures on the solar surface. The ever important problem of topologically complex random and non-random magnetic fields. Relaxation topological complex configurations. Now, this area, the dynamo theory has become mature enough to allow closer connection with problems of this type. They need to be connected closer to the dynamo theory, mainly with the fluctuation dynamo theory. Vorticity production looks to be, we take it for granted that, all flows will be vertical. Common law of turbulence is a vertical turbulence, everything will be vertical. But this attitude, in fact, is similar to the attitude of astrophysicists who say, magnetic fields are everywhere. No need to worry about them. They are everywhere. Don't worry, they will be here. So, in this sense, the statement that don't worry about vorticity production is very similar to this attitude of magnetic fields. There is a conservation law, there is a angular momentum conservation law. It's conserved. So, if there is a significant vorticity, and you need to explain where from it comes. In cosmological context, it's a major problem. It used to be and still remains a major problem. And sometimes, in a late time, not in cosmological context, this can be an important problem as such. And then the last two lines are about observations. Again, I started here about the emergence of magnetic structures. And my main reason why I put it the first is the need for a closer link between solar physics, between observations and theory. In solar physics, the observational data are absolutely fantastic. You can't imagine anything better than that. Absolutely lots of space missions, stereoscopic views, high resolution, all wavelength ranges. If your wavelength ranges, remember the last meeting about solar magnetic fields. How many observational plots were there? One or none? Or maybe two? And this is bad. with this fantastic observational data, working without close contact with observers, is shooting your own food. So it's very important that this work about measurements of the solar, of the current electricity on the solar surface, and then there was a paper of Axel Kandel and Andre Ballon, right? Measurements of current electricity in the heliosphere using the spacecraft data. We do need more works like this. And Doppler imaging for thermoelectric field. This subject has become mature, confident, and obviously I think that it has a great future. Now, numerical simulations have become almost as complicated as the nature itself. And it's important that we treat numerical results in the same way as we treat observations, meaning carefully. I think most journals now won't publish observational paper where only images are published, without analysis of observations. This criteria should apply also to numerical papers. Careful analysis is always required. The colorful pictures is only the first step in your work. It's only numerical. At the end of the day, computers are just a tool to understand physics. In this sense, I think that the importance of the test field method cannot be underestimated. These arguments will continue. How reliable are the results? How general is the method? And it's good. Any method has to, there are no perfect methods on the one hand. On the other hand, any method will continue developing. It will never be perfect. But what is important is that we started applying rigorous, mathematically sound, justifiable methods to interpret numerical results. And likewise, I think that wavelets, which were presented by Marie Farge, also have a similar potential. It's a very powerful analysis tool, both for experiments, observations, and simulations. So, what? Again, these are all my own private opinions. Looking into the future, I think it's important that we discuss the new experiments, because the liquid metal experiments have changed the phase in a very short period, have done a lot. They have changed the phase in dynamic theory. No need to argue to how important they are. Therefore, we are all interested in getting them right, making them, having them prominent, having them interesting. So I think it would be important if our community as a whole is involved in suggesting the ideas for new experiments. I spoke once, discussed it with Gary Forrest, who reasonably said that you will not get money if you just promise to build a new installation, new apparatus, which is just 5 times bigger than the previous one. And you will do the same, but in a bigger apparatus. You need new ideas. And new ideas, different people look differently, but I develop new ideas only when I talk to them. This is where new ideas are born. So I think it's important that we do plan spectacular liquid metal experiments for the future. The ones which you can, as Ulrich put today, which you can sell to politicians, not to us. We are easy prey. We shall easily appreciate the importance of some specific efforts. But we need to, but an experiment is expensive. You can, well, convincing us in their importance isn't even the first step. You have to convince those who have money. And these are people who don't understand science. So we all are interested in suggesting spectacular ideas for MHD experiments. The ideas which will be described on in New York Times, for example. Not even in Nature, but in New York Times. Well, whether we like it or not, but it's life. This is life. Otherwise, we can forget about it. Nobody will give the money. quantitative duplication of numerical experiments. I think we are moving along this pathway. I think it should be developed further and further. And then, now most students, undergraduates, those who like computing, they neglect analytical methods. They don't see the value of them. Why you need all technicals, all these integrals? Take Mathematica, press the button, and you will get the integral calculated. Or you will take the final differences, you will get the number, 27. Why you need to evaluate it analytically is pain and blood, sweat, and tears, and then substitute numbers, and you get the same number, 27. No, this is not true. And we saw it in this conference, that numerical methods, whatever the computers will have, they will be always limited. We shall be always using computers to their limit. This means that the results will be just on the verge of being acceptable, of reliability. Otherwise, it's not interesting. Getting 100% reliable results, these are what engineers are doing. They are doing this to design bridges which will not collapse under the heavier car. We shall always be working on the verge of reliability. We shall never be confident that numerical results we are getting are reliable. Of course, you can always, well, most often, not always, double the precision to check the convergence, but it's only one of the tools. And I don't think there are better ways to do it than by comparing with analytical solutions. Therefore, the better are computers, the more important is analytical work. Not less important, but the more important is analytical work. Next, and this is connected with the mental experiments. The money comes now into spectacular projects which involve spacecraft, as you showed this, the launch of the space shuttle and stuff like that. This is where the money goes. And I'm already working in astrophysics. I do feel that unless you are closely connected with major projects like LOFAR, SKA, Kepler, whatever else, you have no money, you have no postdocs, and you have no PhD students, and you are unable to work yourself, right? After the age of 30. So, if you want to continue our research, we must be connected to major astronomical and geophysical observation programs. Again, it will help to develop new ideas for the experiment. It will help to with bringing new ideas. So it's not a thing we should do only because we must. It's a useful thing being connected to this experimental work. And the last item, again, it's a continuation of that. What the point which Ulrich was making, whether you like it or not, but we should start speaking to people in the street, to politicians, because money is becoming more and more important. The times where we could do what we wanted are passing, and I don't think, whether we like it or not, they will ever return. In the 19th century, in Britain, and also in Germany, many other countries, gentlemen were doing excellent science, using their own money and their own laboratories built in their manor houses, or in 18th or 19th century. It wasn't possible in the 20th century. In the 21st century, we should have been able to do science in our own offices in the universities. Because you need postdocs, you need PhD students, you need access to computers, it all costs money, and they will stop giving money just because you're asked. You have to prove that you deserve any money. It sounds very sad. It sounds depressing. But on the other hand, I would agree that talking to small kids, it's nice. We see these eyes, you know, they're small children who will become, or will not become, depending on you perhaps, scientists of tomorrow. They will come to sit in your office when you will retire and maybe even die. Somebody have to sit in your office, right? Who will that be? So it is, and but less pleasant is talking to politicians, obviously. But there is no other way out. So on this sad note, I will probably say that this is all my summary. But I thought first about trying to organize discussion, but then I realized that if I have a chairman, we can have a discussion. Thank you.
Well, thank you, my brother. That was magnificent.
Was it?
Yeah, very good.
Oh, thank you.
Very good. And so, luckily, he's left his biographs here to give us some inspiration about which topic we should start with. Has anybody got a spontaneous idea of which of these topics they would like to say something? Yes, thank you.
I mean, this connection with big observational facilities, LOFAR and stuff. I mean, we had this discussion a few months ago in Bonn. Alfio Bonanno, who has left earlier this morning, was making this point that one needs to be involved strongly in all these different efforts. And then Günther really, on the other hand, thought this is just crazy to be involved. I mean, he himself being involved, and that this is important for everybody. I mean, should I be involved in all these different? I mean, should I get my name on these papers with other hundreds of people who are making? And then you write something, and somehow you have to be on that paper, or you have to. You're developing an idea, and you have to submit this paper to this consortium of observers. This is all a very strange construction nowadays. And is that really where we're going, or is this just where some of us are going?
Axel, I think that here, like any phenomenon of life, it has different aspects. You described the most unpleasant aspect of that. Well, my experience, Newcastle is now a member of the LOFAR consortium. And we do not try to become politically influential, no. But we do want to have access to the telescope. We do want to have access to make sure that there will be observation programs which we formulate, and we shall have access to the data, direct access. And not also important, when I was submitting my grant application, I wrote, Newcastle is a member of LOFAR consortium. Just being able to state this fact. And we are not a formal members. But then, the disadvantage, because what you described is just very often, not always, but very often you will be able to decide whether you want to jump into this political mud or not. Very often, not always, but often you will have. But what is unpleasant there, that you have to be prepared to do what is needed for this consortium. No, because we are all used to solve problems which we want to solve, which come from inside. There, for example, all of a sudden, especially in preparatory stages, somebody will come to you and say, we need to model the response function of instrument number 27 to some bizarre phenomenon. And then you have to stop doing what is much more interesting to you and start doing calculations there. This is the only disadvantage that I see in this, that you lose some of your research freedom by joining consortium. But you know why you are doing this. There is always a price to pay for the benefits you get from the consortium. Of course, there will be a price to pay for it. But the danger is there. Yes, these papers with 100 authors, where everybody discussed to which paper to refer, and everybody hates everybody else. Of course, it's all there. Of course, it's all there. But what can you do? It's life. It's life, whether we like it or not. But we need to leave it as it is.
Right.
Maybe a few words concerning observations. There is, in geophysics, there is an increasing activities about data assimilation from the magnetic measurements. So in geophysics, there is an increasing activity of data assimilations from the magnetic measurements from satellites. And so maybe it is a way to a link with observers that our community can, in which our community can be involved.
Yes, but in the Earth, with this observation, there is the same problem as in the Sun. This thick mantle which is between the observer and the interesting place. It's the same as in the sun. This thick convection zone on transparent, because what they observe on the surface, it's very hard to guess what is there inside from those data. Of course, this is the inherent difficulties with solar observations and
absolutely, but this is. But however, this, for example, in Grenoble, some of us are involved in some models in order to try to guess what the core flow is, what the magnetic core is from these magnetic measurements. And okay.
Yeah, these are interesting problems, right? Not that it's a boring, physically boring problem. These are interesting.
And we work on true data.
Thanks for this keyword. Data assimilation. There is an Oidal school between the 26th and the 30th of April, connected, which is to be forming the beginning of a program that lasts all the way until the 28th of May. At Norwegian.
Well, thanks for this contribution. Anybody else want to make a contribution to this discussion on this topic? This particular topic about politicians and money and so on? It looks like not. I'm particularly interested in your
I think it's a really huge problem. A lot of parts are very different. The public, the politicians, the observers, and the people who do theoretical works. For example, in solar physics, my opinion is there are so many new solar telescopes and not enough people who do the work with it. Not enough people who have ideas what we really want to look for. So, if you have a good idea what you can do with your dynamo theory, you have to go to the public, you have to speak with journalists, they have to bring out your ideas, and then you can contact observers and bring out a program in which you can work together. It's a long process. And I think it could be very important for each institute to have someone who knows the science, who knows how to come in contact to the press, to the people on the street, to the politicians. And it is a hard job to do that, but I think it could be very, very important. Not a young man, someone who has learned a lot in his life, who knows how to do it, and I think that's very, very important. As well for teaching, you know, young students have to learn how to give a good talk, have to learn how to present their results to the public, to the politicians. I think so many different aspects, we have to discuss them, and they're important. Maybe you can solve the problems you have. And I think you're right, if you have a program with 100 names on it, it's not really interesting. But don't stay in an ivory tower with your science. You have to go out. I think that's important. More today than in former times, maybe, because financial problems and things like that.
Thank you. Yeah.
Not only financial problems, a problem of education. We should keep scientific, how to say, education in school, and even increase. And when we start in Israel to work with young generation, in order to, in order to, how to say, to explain new generation, future politicians, future engineering, how important exact science as part of culture, by the way, not only base of industry.
Thank you very much. Yes. Any more comments?
The method of, or the pathway of getting to public outreach activities is a difficult one, I think. The one that I have observed with some interest is the one that they are pursuing in Santa Barbara, and that we plan to pursue ourselves in connection with future activities, and that is what they call journalists in residence. So these are science writers who come for a certain period of time to one's institute, to do their normal research, or to do their normal paperwork, to do their normal emails, but to write also other papers, and of course which are papers in Nature, for example, or in Physics Today, or in American Scientist, or New Scientist, or other more local magazines like Stern und Weltraum or magazines. So that is another pathway to establishing contact with the science writers. And I think it's an interesting aspect for the two sides. On the one hand, we get to know, as a scientist, we get to know what are the main difficulties in communicating with the public and even with science writers. And they, on the other hand, get an idea of how it is to get the most out of the scientists. For them, it's a new experience, being exposed to the work of the scientists. So to listen, for example, to the confusing seminars that they have every now and then, or all the time perhaps, and to see how the scientists are arguing among themselves, and how happy they are when they finally get a paper accepted, and all these kind of things perhaps. So this is a new experience for the science writers who may not have that experience to the full extent. And that's at least something that I'm not making up myself, but that's what I heard from one science writer in Santa Barbara. And you look with big eyes. I think it could be also good for Rosendorf.
Thank you very much. Yes.
Yeah. Also trying now in Newcastle, I think we shall start with organizing a sequence of lectures for the general public and school children in the planetarium, where of course we shall be also discussing our research. But at the end of the day, maybe this problem isn't that complicated for the kids and general public. Because the problem is not that they don't like what we are doing. They don't know what we are doing. The idea of us for the general public is the idea of the comic movies, where we are all considered to be these idiotic professors who constantly forget where they put their keys and spectacles. This is what the public think we are. So maybe the problem isn't that just changing the negative impression. There is no impression, no information. There is simply people who pay our salaries don't know what we are doing, who we are, what we are doing. So perhaps the situation isn't that bad. We simply need to go out and explain to people why we are doing that. They will not necessarily be negatively received. Not necessarily.
Thank you. Well, that was a very interesting discussion. Shall we move on to another topic now?
There's something more scientific.
Well, yes, it's slightly depressing. Yes, I was interested in what Anvar said about liquid metal experiments. He was saying how we have to do something really fantastic to make people aware of these experiments and get people excited. But actually, although I agree with him, the thing that strikes me about the liquid metal experiments, especially the large 3-meter device that Dan Lustrop is charge of in Maryland, this experiment can be terribly useful to us, especially in understanding turbulence in liquid metals. There seems to be no other way of getting insights into these processes. I mean, best computers can do is to get to magnetic Prandtl numbers of something like 0.1, and yet the Earth and I suppose other planets have 10 to the minus 6 as their magnetic Prandtl number. In fact, theoreticians are absolutely unable to get into these parameter ranges, and I think this is a very exciting aspect of those experiments. I mean, those experiments may never work. They're designed to be a dynamo. Nobody knows if there will be a dynamo, and some people are saying they'll never regenerate magnetic field. But I don't think that's the most important thing. I think the important thing is we will get insight into into experiments with liquid metals with magnetic Fresnel numbers of 1 over a million. So, anybody like to pick up that theme?
Maybe I can speak only for Rossendorf. I think we all should support the activities which are still running in Cadarache, but also in Socorro with the Alpha Omega dynamo of Stirling Colgate, and in Madison. I think Kerry Forrest does a very great job to extend everything to plasma experiments. This is also a new development, and of course we should support also Den in Maryland. Concerning our things, I said it already, we plan to make one big experiment where we can study all sorts of MRI and Taylor instability together. I think it's worth to do. And I would like to urgently ask you to support us really numerically for the precession experiment. I think the precession experiment is risky in many aspects. It's risky in the financial aspect. It's risky in the basement aspect, in safety aspect. But the most risky thing is we do not know if it's if it will work. And so we have simulations from Paul Roberts and Wu. We have first simulations from Tilken, and now simulations come from Caroline Noor and Jacques Léonard and from Krause for the cube, which is really funny. We need more simulations. Might it be to PM 0.2 or something, but we need more simulations on supercomputers to get a better feeling. I think it's really worth to do it because it's very exciting. We have seen for some precession rate you have the Kelvin modes, then nonlinear interaction starts. You have a quasi-laminar flow with a few modes, and suddenly you get homogeneous turbulence. I think it's a terribly exciting thing to build this experiment. I cannot promise that we get a dynamo. We hope that we get 2 dynamos, a large-scale one and a small-scale one, but we do not know. So I would really like to ask you to help us with numerics on this. And of course, if you have other ideas, I heard today about shear current dynamo. Shouldn't we do something like this? Leading a strong current, making a shear, doing experiments on this. So we have the power sources now also. We should keep in touch, Igor, about such possibilities. So new ideas are always welcome.
Again, in this connection, I agree with Paul, but that with these installations, like any good experimental apparatus, it has many functions. For example, there is this controversy now about the nature of Allen wave turbulence, anisotropy of turbulence, spectrum of turbulence. Can it be done in the laboratory? Why not? I don't see why. Again, you can drive turbulence not by complicated instabilities. You can drive it like Greek turbulence in liquids. I understand there is all difficulties with measurements and stuff like that. You cannot just swim in liquid sodium. I do appreciate that. But you are the best. You are the best at experimenters. It's hard, but so just a simple thing. You don't need dynamo, you don't need fast rotation, you don't need cubic meters of liquid sodium perhaps to study turbulence, emission turbulence.
You need larger RM, right?
Hmm?
You need larger RM.
Well, RM can be significant. Well, start with relatively small RM. At least it will be comparable with your simulations, right? At least if you think that simulations which have RM equal to 100 or 300 are useful, experiment with RM equal to 50.
Yeah.
So it will be useful.
Yeah, useful, yeah.
For anisotropy, it's useful.
Oh, yeah.
Anisotropy, they get the anisotropy.
Well, at least we have what Peter Fried was saying about measurement of turbulent diffusivity. Okay, it's just 50% with a molecular one. But these are valuable 50%, right?
I'd like to comment on this also on this discussion. I'm doing myself simulations and know quite well that these run in the wrong parameter regime, as you pointed out, Paul. And I fully agree that it's important to do experiments, for example, to study conditions with low magnetic Prandtl number in particular. But there is some danger to have only one parameter in the right regime and all the others false. So there's also the thought that it might be better to have parameters in a correct ratio than lowering just the magnetic Prandtl number and have, as Axel mentioned, for example, the Reynolds number which is far too low, or if I think in terms of the parameters used in geodynamo simulations, much too low a Rayleigh number or too large Ekman number. So there is some risk also involved in following this path. Another aspect which may contribute to this to a solution that simulations run in a wrong parameter regime is to think about scaling laws as Uli Christensen did in the past, and to derive scaling laws from simulations and to test them with objects which are more realistic than our simulations are. So maybe this is another aspect to discussion.
Yes, it's an interesting area. Does anybody else want to make a contribution to this area of experiments with liquid metals?
I think I've seen often that from the theorist point of view, one would like to ask certain questions and want to go to the experiments and ask them, can you find something out about this and this? And normally the answer is no. But then on the other hand, you just listen, so what have you found? And then all of a sudden they come up with so many different new things, which nobody has ever thought about from a theoretical point of view, that you really ask yourself, so why the hell did I never really think about all these kind of things that all of a sudden pop up in these experiments, which never popped up in simulations so far.
But actually it's normal. I have a similar experience with
Yes.
Rainer Beck, astronomer. It took 10 years to develop common language where he starts asking me questions which I can answer and where I can understand what he's saying. Of course, it's not easy.
Yeah. Right, I fully appreciate that. And so I think the way to facilitate that, at least for me, has always been that I get myself closer involved in at least seeing the experiment, how it really works, rather than just seeing some cryptic picture in a talk. It's such an experience actually to hear and to listen to this thing. I mean, when I was visiting this Karlsruhe experiment, that was really a lasting experience. So it's really like doing a simulation on an analog computer, right? You first make sure everything is set up and the liquid sodium gets hot enough, and then you start pumping up the thing, and you hear this rattling in the whole building, and then you measure your Gauss meter. And then you measure your Gauss meter, and this gradually goes up and goes higher and higher. And the same with the Riga experiment, of course. So these were two great experiences that I've seen. But I've also enjoyed very much seeing the experiments both in Rossendorf for the PROMIS experiment and the many other experiments that they have been doing, and also the PERM experiment. So I think in that respect, I think it is important for us to be exposed more closely to these experiments. And it certainly helps to have more meetings, especially at sites where you can actually see these experiments. I don't think there has been a meeting in recent years in Cadarache, but that might be a very interesting place to see, of course. And Maryland, I don't think so either, and Wisconsin. I have not been in such places.
You know, Axel, what you said about the RM, possible values of RM, for if you want to experiment with turbulence. I think you can get higher values than the present experiments, because now the experiments all are aimed at dynamo action. Therefore, they want high RM in the middle, but I want only high RM behind the grid, for example. Can we estimate that maximum possible RM? For example, new experiment, where is Frank in that? Because what is the maximum velocity? Imagine that you want to create grid turbulence in liquid sodium. You have a jet of liquid sodium, a pump. What will be the maximum velocity? Then, of course, it will be important what grid you take, what is the velocity, and I won't be surprised. Well, is it possible? What do you think? What are the values of RM you get now?
In
10, 20?
In Riga, it's 20.
20. But imagine now that they don't care about this chemical flow. They don't need it. Instead, they pump this liquid solid at maximum speed through the grid, through a grid. Can you get 100?
But this has been done by Alemanni many years ago. Such a grid.
Yeah, but this RAM is based on the size of the system and rotational angle velocity and something like that. Real RAM should be based on the turbulence parameters.
On the grid, yes. Grid
Realize
size.
velocity,
Grid size.
maximum scale.
But I can take a grid with the size of the window.
But you should build huge installation for this.
Yeah,
You can see now laboratory, this side of grid, but
Fine, where are the results then?
no result of course.
Yeah, everybody said there were experiments, somebody did this, this is our laboratory. Where are the results?
It's again, it's velocity.
Here is my hand, give me the paper. What is the spectrum of turbulence?
In our
Given
case,
with some
K
approximation.
to the
we
minus.
perform experiments.
How anisotropic it is?
Yeah.
Don't tell me that you have it. Give me the answer.
Yeah,
No,
we
complete.
have answers.
5 divided by 3 we've got in our
Yeah,
experiment.
we have.
Reynolds about 300 and we've got very
So,
nice.
but I don't think it's impossible. Obviously, there will be limitations. There is nothing without limitations, right? But let's think what we can do. Again, it's only one of thousands of possibilities. Why should we be so much focused on dynamics? Dynamics are fantastic, of course, but they are hard to get. We should also think about other byproducts which we can get for free from these fantastic instruments that we already have.
Well, good. That's a lively discussion on this. Are we finished with this topic? Should we change the topic again? I mean, I was interested in what you were saying about experiments only giving you one parameter, like magnetic Reynolds number of 1/1,000,000, and you have no flexibility in experiments. Well, I see the same thing in theory. I mean, Anwar was saying that analytic work has a role to play that's underestimated nowadays, where people rush to a computer and produce a solution. But only in one case. I mean, the trouble with computers is that they don't survey parameter space. They take individual spots here and there and try to join them up in some sensible way. I mean, I realise I'm overestimating, or I'm saying it in a too extreme way, but this is an interesting aspect that Anwar introduced in his summary, and I wondered if we could pursue that at all. Has anybody got anything to say about analytic work versus computational work, the role that analytic work can play, etc.? Let's start. Very good.
I'd like to say, when we started to work with Axel and starting to check analytical studies, it became more and more exciting, because interaction analytical people with numerical simulations is extremely important. And I think that it gives new ideas, and of course it's also some people will try to have students which perform analytical studies, and of course it's very important and it's extremely beautiful things.
So,
Add to that?
sir, I had a discussion with Professor Ulrich Frisch in this particular aspect, where he suggested I should do multi-scale methods to understand my inverse cascade model, and he suggested to get to that particular point where you really understand multi-scale methods from this point where you are and develop a model. It will take 3 years, but the postdocs are having a task in hand. In 1 year you have to do this work and produce papers. So the postdocs are not getting the freedom to learn new things or develop mathematical tools because they are already having a task in hand. This was his comment. So the work division should be a little more generous so that postdocs can learn, or students can learn the analytical works along with their regular works.
Thank you. This is an interesting aspect about whether we who advise students are advising them well. This is what has been said. I mean, does anybody have an opinion about this? Are people being advised not very well by their advisors?
I mean, it sounds like his comment was less about the quality of the advising than about the absolute logistical problems.
Yeah, exactly.
That you have maybe 4 years of research as a graduate student. There's a limit to how much you can learn there, but you'll learn a decent amount. And then you go to a postdoc, and you are, if you are not that lucky, you're applying at the end of your first year of your postdoc for a second postdoc. And if you're lucky, you're applying at the end of the second year of your postdoc for your second postdoc.
Exactly.
And that does not give you time to learn anything that needs more than about 6 months to learn.
Yeah, exactly.
You can cheat a little bit in there. Maybe you can learn something over a year, but you're not going to learn anything that takes 2 years.
Yeah,
it's really irrelevant.
True. Nodding head there. Anybody else got anything to say about this?
What can you do other than get like 5-year positions? At which point 2 or 3 years is okay, but anything more. I mean, think about the idea of coming in. Maybe you want to write a code. You can't. It takes too long.
Maybe you shouldn't. I mean, which project does really take 2 years to learn? I mean, I think the best way to do that is to get together with the relevant people who actually do such things already, to have a mutually productive collaboration with somebody who knows exactly what to do, and you have your part to add to that. And that way you learn fast.
Well, this is risky for me to do, but despite having done my undergraduate studies with Eric Blackman, I came to Nordita 2.5 years ago, knowing no MHD. Axel, what's your analysis?
Yeah, very positive, because you did learn all of MHD and made major progress. So what the hell are you talking about?
I felt that it took me a while, and I was definitely just. I'm still learning a lot that I really think it would have been very useful for me to know a while back. But I guess if you're saying that, well, thank you, but it was hard.
Yeah, that's...
Alex, you are talking about the whole system, right?
Yeah.
Of temporary positions.
Yes.
The whole system of temporary positions.
Yes. Yes. Because my background is different.
Especially 2-year positions. I think already 3 years helps a lot. Because then, if the 2-year positions, you're applying at the end of the first year. And that means you have to get publications out in the first year, and projects with a lifetime of 1 year are already a very big problem.
Well, at least some gradual change perhaps can be done. If you, for example, when we apply for our grants, trying to apply, not necessarily for very short stay, but say at least 3 or perhaps even venture 4-year postdocs. The chances will be lower, but what can you do? But I see the point. I agree with you. I see the point.
Well, I've done very little numerical work in my life, and I know the numerical work I've done is always, I felt ill afterwards. And but what I can say about analytic work is that it's hard, and it takes a long time to do it well.
Exactly.
It takes a very long time to do good analytic work. I mean, it may take 1 year or 2 years to write an analytic paper. It's not something, rush off to a machine, get some answers out. It's a very long job. Understanding the problem, knowing the techniques that you need to solve it. It's not something you can do overnight. You can't sit down and say, in 6 months' time I'll write a paper. It usually takes 2 years to write a paper.
Yes, sir. This was what Professor Ulrich was pointing to me. Gerald Frisch was pointing to me, that you may need 2 years of training before you come to a level where you can develop a theory. This is what he told me.
I mean, it's a major investment in your time to do analytic work.
But it's only if you work in serial. And Axel was suggesting to work in parallel. Okay. And then accelerate. But you know, but my experience, you know, this analytical work will take 2 years if you are focused on analytical work. But if you work with the numerical people, and they bring to you results which look plausible, look to be worth of an effort to explain. Then there will be lots of ideas where to start from numerical
Well, I've
data.
done that.
And then your analytic
still
work
takes time.
will take 6 months.
It still takes a long time.
No, but well, it depends, of course. But the working together accelerates things enormously. And you know, Alex, another thing what Axel was saying, I will just put it in different ways. The best way to learn is to work. In this sense, you shouldn't think that you should go to the library and spend there 2 years reading impossible books and then emerge from the library and solve the problems, right?
I agree there. But at the same time,
I would like to say that you paint a depressing picture, but it doesn't get any worse when you get older. I've been here at the University of California. I've been in a system which rewards publications. Your advancement depends on it. Your grants depend on it. And you don't get time to read all you should read. It's a perpetual problem. What's worse for you is that security depends on it. I mean, unfortunately, I don't worry about security, but this is the essential difference. It never stops in academic life. It always goes on. Well, I think we've probably exhausted that topic.
I was wondering.
What do we go on? Sorry?
I mean, I was wondering whether this it sounded a little bit pessimistic, especially what Andrew said, that it really takes 2 years to work on a good project.
How long have we been doing that?
it depends. I think
it's
there's
certainly
just
true that I have also papers which started at some point and finished 12 years later.
I think the big
which finished 4 years later.
Doing a routine algebraic calculation and having an innovative idea, because the idea comes slowly. It takes a very long time for that idea to develop.
But I remember at peak times when Gene Parker was writing his papers, he had easily something close to 10 papers a year. And so how was that possible? And in view of what we just heard here.
Well, it depends on the nature of the project you're attacking. A lot of the papers I've written are where I'm simply exploring new phenomena, and you take a look at it and size it up and can do some useful calculations in a matter of a couple of weeks and then write a paper on it. I mean, that's... I've never been involved in a big project, and I appreciate the difference, having seen the results given at the meeting. Times have changed. I don't know what else to say.
Yeah. Thank you very much. Yes. May I say, yes, another thing is that a good analogy, I think personally, is with cooking. I mean, when you're cooking a complex dish, you have many pots on the cooker, and it's good to have a number of things to cook. And you suddenly remember something, it will be useful, you bring the pot from the back to the front and you work on it. And you know, it's good to have projects that are many levels of development.
Okay, actually, there's one other thing. I don't know whether this is unique to me. Conferences in MHG have become a lot easier for me. Because originally, everything was new to me, and I had to spend a whole lot more effort to follow a talk than I do now. Admittedly, sometimes I don't spend that effort. But at the first few conferences, I couldn't spend that effort for every talk at all. As you get, I guess, more experienced in the field, the idea of multitasking becomes much easier and much more plausible because you've already, in a sense, done a lot of that multitasking already. So, for again, for the junior people, it's harder to do. It's harder to do those things, those tricks.
But it's good. If it was easy, you would never do it, because you are challenging.
Give me easy.
But Alex, we all have lived through the same stage. It's common. It's from generation to generation.
A remark to a side aspect, especially when it comes to the situation where a young person which has not that much time has to learn a new method, say, new analytical approach. then it is extremely important that the papers of the people who presented this method or initiated it are extremely transparently written. And this is not always the case. And I would encourage everybody to invest more in this place who is doing profound analytical work.
On the other hand, Matthias, we've been working on the test field method, and I don't think we've yet figured out how to explain the test field method quickly and easily. And we've been trying really, really hard to explain it, because it's always been an issue.
I would easily include myself in this demand.
Anybody else going to say? I mean, how about the people that are staring at their laptops? Maybe they've got something to say.
Well, so I guess something I want to say is it seems to me that at least in the recent year, a lot of people is doing cosmology, and actually people in cosmology they always say that when you go to a room, look at the age of the people, then you realize if the field is healthy or not. Yeah, so that's unfortunate. But I have to say, I guess one reason is for cosmology because there are so many things that are unknown. So for a student, he can just walk in, maybe learn the thing for half a year, and then he can just write something that's completely new, and that's impossible for MHD turbulence. So.
Yes, it depends on subject, doesn't it? Yes, that's true.
Two keywords have fallen. One is multitasking and the other one is laptops.
Yes,
so how do people deal with that?
Yeah.
Well, I think laptops are a good way to multitask.
They're good for sitting in a lecture and just looking at you, catching up on your email and things like this, you mean?
It's not that the people in the laptops are really not paying attention to what is happening in the lectures. Sometimes it is very useful to look at a reference that the speaker is actually saying. And by the time the speaker finishes saying things, you already know the paper and have seen what he has been trying to say there.
You say this, but I sit in the back watching people looking at the laptops. The last thing they're doing is looking up a reference. Simply not true. It's very rude, in my opinion. Anybody else like to contribute to this? So, how about the other topics that some of the lists are here? We've said a lot about some of these issues, well, just about 2 or 3 of these issues. Anything else?
The next one is astrophysical, geophysical observation progress.
Sorry?
I think very important last topic.
Yes. Connection with geophysical and astrophysical observational programs.
This is a cynical aspect of this, meaning where the money is lying.
I think it's not only a question of money, it's a question of interaction between astronomers, observators, and people as we, for example, to build sample models of stellar and solar activity will be very good. Because yesterday, my feeling was that from one hand, existing wonderful observation of solar-like stars from one hand, practically no reasonable theory, old, no non-linear problems. We should make together with astronomers simple sample, maybe routine calculations, which, start from standard model of main sequence star, and after that to build reasonable dynamo models.
Yeah, I'd like to add in your sense that, of course, dynamo theory was very much inspired by solar physics, but I think that stellar observations will open a much wider parameter space, and there will be many interactions with numerical simulations, because you can really do observational parameter studies and compare these with numerical simulation.
Fortunately, we've got dynamo number. This dynamo number, it is collect turbulent diffusivity, differential rotation, and size of star. And what we should do, we should, for each spectral class, to build critical dynamo number to find, because it depends on the ratio more or less of how depth you connect your zone, because relation to position of maximum of alpha effect and so on, and at least compare theory in massive way with observation.
Thank you very much. Yes. Well, I think we've had a long and interesting discussion. I think probably the time has come to bring it to a close. And this meeting was largely in honour of Karl-Heinz, and he will have the opportunity now to say something about this meeting.
Yeah, I can only repeat the words I already said. I enjoyed this meeting very much. I thank all of you for your for your kindness and for all the kind words you found about me. Yeah, thank you very much.
Before finishing, I think all of us will want to say more thanks to Axel, who has been, well, we deal with liquid metals and mercury. He's been like mercury, flowing all over the place, fast, solving every problem. Fantastic.
Thank you, Paul, but we should also think, of course, those people who have made it possible. Especially an establishment like Nordida is extremely important for being able to do these kind of things on a fairly normal basis without my too deep involvement. And so the thanks go also to people like Hans and Anne and Daniela and the three students, Anna and Emma in particular. So thank you to those as well. All right. Any questions? Otherwise, I wish you all a great way, safe way home.
Вот, ну все, в понедельник выйдем. То есть, потому что у меня глазу. Нет, то, что стояло, да. Тут я вам покажу еще раз. Они вполне вы решаете всего два урока. Одно это другое да.
And the first chapter of that is described the first section. I found it very clear that once I read it together, then In the sense of, as opposed to running. So that is the idea.
And it was really for me. When I decided
И увидят, что они те же. По-моему, они те же. Сейчас я закрываю. Да, рассказывай. Я не хочу. Да не ори.
So maybe we see us in October, but
yes, of course. I will send you my email slightly.
And I send you the
Yes. Yes, and maybe I'll send one of our most which translate to English. It will be interesting to see what actually happened, what's allowed. Maybe we'll just, I'll discuss with people involved in this work. I mean, we should do something for Germany, because it's very common in Israel. Yes, it's good possibility to get one.
Goodbye. Maybe we see us in Japan. And kind greetings to Tetsuya Masada. Oslo. Solo Oslo from Germany. I was there. I met him there. Do you meet him sometimes? We had a discussion there and we spoke a little bit. He tried to speak German once again, so that was nice to hear. And what is his name? I've spoken with him, but I even remember him. Yeah?
Yeah, astrophysics is the best. But the problem is for the teachers. The old teachers, the younger people don't come into contact. I'm trying to do my best to find some teachers who want to. And the program in school is shortened as well, so the young teachers have their problems to learn what they have to teach, and so they have not enough time. The program is very concentrated. What we have to do in former times was much better. They've shortened the time in school for one year, so that instead of 13, 12 only, because in America they have the same. It's not. Yeah. Yeah. And if the pupil likes very much I give lessons to kids in the school, higher classes, to their problems. And I found out I always ask him first, what about your teacher? And when he says, oh, he's not good, then I understand. If they say, well, he's good, he's pretty good, then I find out because they are friendly, but I can't explain the thing very well. And I think didactics is an important scientific thing. I'm very much interested in it. When I was 13, I said I want to be a teacher rather than my teachers have done. Yeah, maybe we need to meet each other someday. I would like to come to Japan once. I tried to contact you before. And Tetsuya as well. I have no more comments. And I contact I'm interested in my Okay. With this